Balancing redox reactions using oxidation numbers. So we're going to go through the steps involved in using oxidation numbers to take an unbalanced equation and balance it. Now, you can balance an equation using trial and error, but it's not a particularly systematic way of doing it. And if the coefficients end up being anything larger than like 4, it's going to be also very time consuming to do it in that way. So for more complicated redox reactions, this method is going to work. And if you can't easily divide it into half reactions, you may also want to use the oxidation number method to do this. So the first thing is to determine what the oxidation numbers are. And then you want to look at, based on those oxidation numbers, which atoms are going through a redox reaction. So determine the changes, the ones that are actually changing their oxidation numbers, and those are the ones that we want to look at in terms of who is gaining electrons and who is losing electrons. So we're going to temporarily balance those redox species. So if we had the way maybe a subscript on one side that has a 2 and the other side there's only one of those things, then we're going to temporarily do it by using a coefficient. We're going to put it in front of it, and that'll make sure that the same number of those atoms are on both sides of the reaction. Now we say temporary because we may have to change this coefficient later. We may have to multiply it to a larger number, but it will definitely be a multiple of whatever that temporary coefficient is. Then we want to see, okay, based on those two things that are changing, one of them is going to be gaining electrons. So we have our reduction gaining electrons, and we'll have one of them being oxidized that will be losing electrons. We want to make sure we know what ratio we need to have these happening in so that the electrons lost are equal to the electrons gained. We need to make sure those are the same number. So if something's losing 1 electron and the other one's gaining 2 electrons, so the oxidation is losing 1 but the reduction is gaining 2, then we're going to have to multiply that by 2 so that electrons are going to be equal. We're going to apply this ratio to the coefficients of the redox species themselves. And this may, if we did use a temporary coefficient, then we may have to adjust that temporary coefficient. We'll multiply it by that. And we're going to be doing this on both sides of the reaction. The rest of it, now that you have 4 of those species balanced, the rest should be fairly easy to balance by inspection as long as you don't change the coefficients that you put in front of your redox species. So the first step that we want to do is to write the oxidation numbers of all the species. We have our element, so it's going to have an oxidation number of 0. We know that oxygen is going to have a oxidation number of -2, hydrogen is going to have oxidation number of +1, and so that's going to leave nitrogen, in order to get the oxidation numbers to sum to give you the net charge as 0 for that thing. So in order to get them to sum to give you the net charge, nitrogen is going to have to be +5. Hydrogen +1 again, and oxygen -2. Over here we have oxygen at -2 again, hydrogen at +1. And so our tin is going to have to balance that out. And so we're going to need a +4 in order to have the +1 times 2 is +2, plus +4 gives you +6 to counteract the -6 that we have in our oxygen there. 3 of them at -2 each. We have -2 on the oxygen, and then therefore +2 for the nitrogen. Now, in terms of the tin here, it's starting out on the left-hand side at 0, and it is going up to +4. And so its oxidation number is increasing from 0 to +4. And the other one that's changing, that we look at hydrogen, and on the left-hand side and the right-hand side, it's not changing. Oxygen is at -2 on the left-hand side, both cases, and -2 on the right-hand side, both cases. But if we look at nitrogen here, it is going from +5 down to +2. So we know that that must be our reduction, and we know that, so this is our reduction. It is the decrease in the oxidation number. Reduction is the gain in electrons. If you're gaining those negative electrons, you're going to decrease your oxidation number. And we know that this one is going to be oxidation. So there's a little bit neater writing. First step, figure out the oxidation numbers and figure out who is changing and who is remaining the same. And then from there, we can identify which one's oxidation and which one's reduction. To do our reduction, that again, our +5 down to +2 for our nitrogen, it's going to require 3 electrons to get that to happen. If it gains 3 electrons, then it is going to be going from +5 to +2. For our oxidation, in terms of losing electrons, to go from 0 to +4 would require the loss of 4 electrons. So we have our reduction and we have our oxidation. We do also want to make sure that our species are balanced, so we can see that our redox species, the tin, there's 1 on the left-hand side and there's 1 on the right-hand side, so that is good. Our nitrogens, we have 1 on the left-hand side and we have 1 on the right-hand side, also good. So if we needed to, we would temporarily balance them. So let's say we had 2 tins on the right-hand side, then we could temporarily put a coefficient of 2 in the front there. We don't have that, so we don't need to worry about that for this question. Now we want to find and apply a ratio to these redox species so that the number of electrons that is being lost is going to be the same as the electrons being gained. So we have 4 electrons being lost, we have 3 electrons being gained. Our lowest common multiple is going to be 12, so we have to apply a factor to those number of electrons to get them to equal 12. So if we get this reduction to happen 4 times, then we'd be talking about 12 electrons. If we get this oxidation to happen 3 times, then we're talking about the loss of 12 electrons. And that would get us our equal number of electrons on both sides. So the key is we have to take the one that is going through oxidation and multiply by 3. We have to take the ones that are going through reduction and multiply by 4. And that's where we are going to be putting, there's a little bit neater writing, putting that factor in, that 3 in front of the tin, and do it on both sides. So we end up with 3 on both sides. And let's do the same thing for our reduction. We're going to be multiplying that by 4 so that we have 12 electrons gained. The 4 is going to go in front of the species that is being reduced. And yes, it is the nitrogen that is actually changing its oxidation number. We're putting the coefficient in front of the entire species that we're talking about that contains the nitrogen. And we're doing that on both sides. So that is going to give us our redox species coefficients, and we're not going to change those. Now all we have to do is balance the rest by inspection, which should be relatively easy, A, because we have 4 done, and B, because we can use those ones to figure out what it is that we have to put in front of our last one. So looking at this one, we could take a look at the hydrogens. So on the right hand side we have 6 hydrogens over here. That's the only place where we have hydrogens. There's already 4 accounted for right here, so then there must be only 2 hydrogens in this water, so then we have our coefficient of 1, and we can double check that with our oxygens. This would give us 12 oxygens plus 1 on the left, so that's 13 oxygens, and on the right we have 9 plus 4 is also 11 oxygens. Not 11, 9 plus 4 is 13. 13 oxygens, that's better. All right, so balance the rest by inspection, so feel free to drop in the coefficient of 1 if you'd like, and you're done. Now let's see one with a temporary coefficient. So if the redox species that we're using is not equal on both sides, we're going to multiply one of those sides in order to get it to balance with the other side, knowing that we might have to adjust that temporary coefficient. And we need to also be aware that the electrons that we're going to be using now are also going to be affected by that temporary coefficient. So if we're saying there's 2 things that are both gaining 1 electron, then we're not talking about 1 electron anymore, we're talking about 2 electrons. So we're going to apply that to the electrons as well. All right, so with this one again, same thing. We're going to start off with, and again, you could probably do this one by inspection, but let's use that as a practice for a temporary coefficient. So we're going to start off with the oxidation numbers for each one of them. So there they are there. We're going to look at who is changing and who is not. Again, the oxygen's not changing, the sulfur's not changing. So we're going to be looking at our aluminum, and we're going to be looking at our copper as our redox species. So for the aluminum, we have it starting out as 0 and going to +3. So it must be losing electrons in order to have its oxidation number increase. We know that oxidation is loss. And so we can say that this is our oxidation half reaction. And then our reduction half reaction, reduction should see a decrease or a reduction in its oxidation number. So if we look at copper, it starts out as +2 and it goes to 0. So that is going to be a reduction half reaction. Reduction is the gain of electrons. That would be copper gaining electrons. So write the changes for those redox species. We're going from, again, for aluminum, 0 to 3. So if we looked at this in terms of electrons, let's put these here. So there's our reduction electrons. There is our oxidation. Let me get this out of the way here. We're talking about, for aluminum, 3 electrons in order to get that to go from 0. We're doing our oxidation here. 0 to positive 3, that's going to require 3 electrons. However, there are 2 aluminums on the right-hand side, and there is currently only 1 aluminum on the left-hand side. So we are going to have to use a temporary coefficient in order to get that to balance. So we're going to temporarily put a 2 in front so that the number of aluminums on the right-hand side is equal to the number of aluminums on the left-hand side. Now that they are equal, we can talk about their electrons. So each one of the aluminums is going to be losing 3 electrons, but there are 2 of them. So we are talking about not 3 electrons, we are talking about, in fact, 6 electrons themselves. So we have 3 electrons, let me just write this in, 3 electrons, and we are multiplying that by 2, so we're really talking about 6 electrons for the aluminum to go through its oxidation. This is our oxidation half reaction. For the copper, just to point that out, we're going from positive 2 to 0, so that is going to be the gain of 2 electrons. So we're dealing with 6 electrons and 2 electrons in order to get these 2 half reactions to happen. So the lowest common multiple there is going to be 6. We can apply a factor of 3 so that we have 6 electrons gained, and for our, let's drop that 3 in there. For our oxidation, again, we have 2 of them. We're going to multiply this by 1. Remember, we've already talked about there being 2 alumina, so that's accounted for. We're now going to multiply the 6 electrons by 1 in order to get the electrons gained and the electrons lost to be equal to each other. So what that means is this factor of 1 is going to be put in front of the aluminums, and it's going to be both on the right and the left-hand side. Now on the right-hand side, there's nothing there yet, so we can just drop in a 1, and that's going to account for the number of aluminums. Over here, where there's a temporary coefficient, what we're going to be doing is we're multiplying it by 1. So we're not ending up with 1 or 21 or 3 or anything weird like that. We are just multiplying it by 1, and so that temporary coefficient becomes a permanent coefficient of 2, and we are done balancing our equation. There's no other species in here to balance by inspection, so we're done. All right, realize that if the redox species is found on both sides as multiples, and so let's say we've had 2 on the right and we had 2 on the left, they are balanced, but there is more than one of them. There is a multiple there because they have a subscript. Make sure you account for the electrons for each of them. So if you're talking about this particular transfer here, we're going from a positive 2 to a positive 3, so we're talking about 1 electron. Be sure that you realize that we're dealing with 1 electron per atom, so we would have to really be talking about 2 electrons. So be careful when you're dealing with those redox species where there are multiples of them. Make sure you also multiply the electrons before you start looking for the lowest common multiple. All right, then there is this issue where we have some members of the same species doing more than one thing at a time. And so one of them, because remember, we're talking about gazillions of these particles going through reaction, and some of them might get oxidized, while other ones of the same species could get reduced or maybe remain unchanged. And so how we're going to deal with this is, so essentially imagine we had species A and it goes through reaction and it forms something that has A in it that has caused it to be reduced, plus maybe something else that has A, so maybe it gets combined with B or something like that, and maybe this other A gets combined with C, and so we might have one that's going through a oxidation, and maybe the other one, and it's the same thing that we're talking about, these are all A's here, but maybe one of them is oxidation and maybe one of them is reduction because you're making 2 different products out of the same species. So what we're going to do with that is we're going to call this additional species, and essentially we're going to be splitting the amount that we're dealing with, because remember, we never really just have one particle doing the thing. We have a gazillion of them. So we're essentially going to split it into two groups, and we're going to deal with them separately. It's kind of like playing blackjack. If you get two of the same cards, you can split them and play the two hands differently. That's kind of what we're going to be doing with these additional species. So we're going to take that whole big group, and we're going to say, okay, let's not treat it as one group. Let's pretend it's two separate groups. And then we can talk about part of that group going through maybe the oxidation, and the other part doing the reduction. And yes, they are the same thing, but we're going to deal with them separately. Once we're done, we can put them together because they are the same thing, so the numbers are going to be add up together on the one side. So let's try that with this particular equation. We've got our reaction here. First step again is to put the oxidation numbers in and look at who is changing, and this should tell you whether you're going to have to deal with this additional species or not. So if we look at calcium, calcium starting at is +2, over here it is +2, over here it is +2, so it starts on the left at +2 and on the right it is also +2, so it's not one of our redox species. Oxygen, as you would imagine, unless we're doing something weird like the peroxides, it's also not going to be changing, so it is not a redox species. Same thing with hydrogen, you can check it out. It starts at +1, ends at +1, it's not changing. So we're only left with one species, and it is our chlorine. It starts out as 0, and then on the right-hand side, there are some chlorines that are -1, and then there are also some chlorines that are +5. So it's the same species here, but some of them are turning their oxidation from 0 to oxidation number from 0 to -1, and some of them are going from 0 to +5. And so we've got this one species, and remember, it's not an individual molecule, it is a whole group of molecules, and some of that group are going through an oxidation and some of them are going through a reduction. So this is what we mean by an additional species within a redox balancing. And so the system we use for that is that we say, okay, well, if we've got this group and half of them are doing one thing and half of them are doing the other, maybe it's not exactly half, but a portion of them are doing one thing and a portion are doing the other, what we're going to do is we're going to write it out separately. We're going to say, okay, some chlorines are going to do one thing and some chlorines are going to do another thing. And so I'm going to write them as two separate species. We're sort of writing them twice. And then we can play each one of them separately and at the end put them back together. So we've got our oxidation numbers. I'm going to say that, and again, these two are identical right now. I'm going to color this one in gray just so that I can say, okay, this is the chlorine that ends up here, and then this top chlorine is going to be the one that ends up over here, just to keep them clear in my head. So the one chlorine is going from 0 to +5. And so it is increasing its oxidation number by 5. The other one is going from 0 to -1, so it is reducing its oxidation number. Let's do that. It is reducing its oxidation number from 0 to -1, so that is our reduction reaction. And then we have our increasing the oxidation number from 0 to +5, that is our oxidation. It's losing electrons, so its oxidation number increases. We're going to treat each of these separately as we go through. So in order to do, let's quickly mention the doubling factor as well. So we've got this idea that on the left-hand side, let's look at this one first, the top one, we've got 2 chlorines, and over here on the right-hand side, we have 2 of these chlorates. So there's a total of 2 chlorines currently on the left-hand side as well as the right-hand side. And for the gray one, it's the same story. We've got 2 chlorines here and we've got 2 chlorines here. So we don't need a temporary coefficient in front. Like imagine like this was just 1 chlorine here. Then we would have to put a temporary coefficient in front so that, oh, that's not the right place. We'd have to put a temporary coefficient here so that the 2 chlorines here and the 2 chlorines here match. Luckily, right now, we're dealing with 2 chlorines becoming 2 chlorines that are white here in color, these 2 right here. And we have these 2 is becoming the 2 on the right. So we don't need any temporary coefficients, but we do need to recognize that there are 2 of them. So when we talk about this, let me get the right color here. When we talk about this oxidation that is happening, the loss of electrons and the increase in oxidation number, it's going to require 5 electrons to do that, but each one is going to require 5 electrons. So it's in fact a total of 10 electrons that we need to get that oxidation to happen. For the reduction, we're talking about 1 electron, but there are 2 of them, right? There's 2 of these guys here. Let's get that in red. 2 of these guys here. And so we're going to have to multiply the 1 electron, 1 for each of the chlorines. So we're talking about 2 electrons required for our reduction. Now we need these two numbers to equal each other. So we have our lowest common multiple of 10. We are going to apply our factor to each one of those. We need to put a multiple of 1 in front of the white chlorines here, and a multiple of 5 in front of these gray chlorines here. So let's do that on the left-hand side, and we're going to carry that through. Again, make sure you're matching it up with the right chlorine. So this gray one here that is going through the reduction is this one here, so I'm going to put the coefficient in front of the species that has that chlorine. Now the one that is going through the oxidation has the 1 in front, so I'm going to make sure I put that 1 in front of this species here because it has the chlorine that is going through the oxidation reaction. All right, so let's clean this up a bit. We have our redox species balanced, and now it's going to be a matter of balancing the rest by inspection. And I picked probably the calcium to do first. So on the left-hand side, we've got 5 calciums there, plus this one here. So there's a total of 6 calciums on the right-hand side. And so I know that we're going to need 6 calciums on the left-hand side. And then we could probably do the hydrogens would be the next easiest one to do. So this is going to give us 2 hydrogens here. Multiplied by 6 is going to be our 12 hydrogens on the left-hand side. And so the only place to make those up on the right-hand side is with the water. So we're going to have to put a coefficient of 6 in front of those water. Now everything's balanced. But do note that this additional species, we can clean it up a little bit. 1 chlorine and 5 chlorines is really just 6 chlorines. So we can add those guys back together. Having played them separately during the reaction, we can put them back together, and we have our balanced redox reaction. Having used these additional species in that it is one thing that is going through 2 types of reactions. All right, so let's try doing 2 of those guys together. We will do one with a temporary coefficient as well as the additional species. So this particular reaction is going to be getting hard to do with a trial and error. Balancing by inspection would take you a little while for this one. So we want to have the systematic way of using oxidation numbers to balance it. So again, same thing, start with the oxidation numbers. And once you've done enough of these, you can probably start realizing you don't really need to write down all of the oxidation numbers. You really only are interested in the oxidation species. So the things that aren't being oxidized or reduced, the redox species, the things that aren't being oxidized or reduced, you don't really need to worry about their oxidation numbers. So you can start taking a bit of shortcuts, but there are all of them. And then you want to identify who is changing. So if we look at our redox species, we have a couple of things going on here. So we have, here's manganese here on the left, and it is +7, and it is going down to +2. So it must be changing. In order to get that, it is going to be gaining electrons. So we know that that is going through a reduction. That says red. And then we have chlorine here at -1, and here it is as an element, and so it is at 0. So its oxidation number is increasing. So we know that that's an oxidation. Oxidation is the loss of electrons, so losing those negatives is going to bring its oxidation from negative over to a less negative number, 0, which is great. But the problem is that chlorine also doesn't change. So this chlorine here, which is the only chlorine on the left, it definitely goes through some oxidation, but it's also not going through some oxidation when it forms these species here. And so we've got the same idea. We've got a chlorine that is doing 2 different things. And so how we deal with that is that we are going to split it into 2 groups, and then we are going to play those 2 groups separately from each other. One of them will do as changing, becoming this chlorine over here, and then the other ones can become the ones that aren't going through that change. So manganese first, the change we're talking about is a reduction, so we're talking about 5 electrons. There is 1 manganese on the left, and there is 1 manganese on the right, so we don't have to worry about temporary coefficients with that one. The chlorine, though, that is changing, there's 1 over here on the left, but there's 2 on the right. So we're going to have to fix that by using a temporary coefficient out front. So we're going to split it, and we're going to put a temporary coefficient. I'm going to play this one, so let me just quickly put this in red. So this guy here, I'm going to talk about as, I probably shouldn't put that in red, let's go green. This guy here is going to be the one that is going through the oxidation. So I'm going to treat it as my redox species. This other group right here, let's actually put that in blue. The other half of the group, and we'll see whether it actually is half or not, the other portion of the group is going to be just not changing, and so I'm treating it as if it's not a redox species. So I'm going to be dealing with my manganese going through a reduction, and my chlorine here, not the one above, going through this oxidation. And then I also have these other chlorines, which are just going to be balanced at the end by inspection. So I've temporarily balanced this so that my number of chlorines is equal on both sides. We're talking 1 electron here, but there are 2 of them. So we're going to have to multiply that 1 electron by 2. And so we're really talking about 2 electrons needed for our oxidation and 5 electrons needed for our reduction. So our lowest common multiple here is 10. We're going to have to apply a factor of 2 to our manganese, so the coefficient that's going to end up in front of our manganeses are going to be 2, and the coefficient that's going to end up in front of our redox chlorines, not all the chlorines, but the redox chlorines specifically, these guys right here, is going to be a 5. So we're going to drop that 5 in front of this chlorine over here, and this 2, the temporary coefficient of 2, we're going to be multiplying it by 5. So let's clean this up and put in the coefficients. So we have our 10 HCl's that our redox chlorines are involved in, and they're going to be forming our 5 chlorine gases on the right. So we've incorporated that factor. We can drop the 2 in front of the potassium, the species here that has the manganese in it, and then this species over here is going to get the 2 as well. And we are done balancing our redox species. So now, let's clean this up a bit. Now it is just a matter of balancing the rest by inspection. So again, try to pick the easiest one to start with. So I would say here, you have 2 potassiums. The only place it shows up on the right is here, so you're going to have to put a 2 in front of that potassium. Then after that, I would say probably the chlorines are the next one to go with. So on the right-hand side, we know we have 10 chlorines here, plus another 4 is 14, plus those 2 is 16. We've already got 10 right here, and we need a total of 16. So we're going to have to put a coefficient of 6 in front there, and then you've got to finish off your waters. So add up all of your, what would be this? Probably the oxygens. So on the left-hand side, the only oxygens are right here, and there's going to be 8 of them. And so we're going to have to put a coefficient of 8 in front of those waters. And after that, we have our balancing done. There's our 6 and our 8, and we can put our 2 HCl's together. The 10 and the 6 can come together to give us our 16 HCl's, and we have our balanced, complete chemical equation. All right. Last one that we're going to look at is going to be a non-integer oxidation number. Now, we know that these oxidation numbers aren't an actual real property of these atoms themselves. It's an arbitrary bookkeeping system in order to keep track of electrons. And so if you're talking about fractions of an electrons, that's not something you can actually have, but you can imagine it existing. That if you had a fraction within a group of them, that could be possible. It's kind of like saying that the average household has 2.5 children. You're hoping that that's not an actual number in any households, but it is an average split between a group of households. Same thing is going to be true for these electrons. We can have the electrons that are being transferred as a fraction for a while, and then what we'll see is once we're dealing with the group of them, we're going to actually deal with back to whole numbers of electrons. But while we're solving it, we may see fractional oxidation numbers and therefore fractional electrons temporarily until we actually apply the whole group to the number, and then we'll see what the actual numbers are. So same thing, same method. Oxidation numbers first, put those in, and then look at who is changing. And this is where you see, once you're doing your oxidation numbers here with our lead, the only way to get our sum to equal 0 when oxidation of the oxidation number of oxygen is -2, and there's 4 of them, so that is going to be 8, but it's split between 3 leads, and so 8/3 is going to be the oxidation number for that lead. So that looks odd, and again, you can't have 8/3 electrons, but oxidation numbers aren't an actual value. They are a arbitrary system used to track the electrons. So we can use that as a temporary measure of the electrons until we actually get the coefficient. So we're going to have a coefficient in front, and then we can actually talk about the actual number of electrons for that entire species. All right, so who's changing? Our manganese, we can see, is going from 2 to 7. So again, its oxidation number is increasing, and so it is going to be losing electrons. That is our oxidation. So let's put that. This is 5 electrons here, and we should double check. We're talking about 1 manganese on the right, 1 manganese on the left. So we are just talking about 5 electrons because there's only 1 manganese each. With the leads, though, it is going from 8/3 over to, there it is, at +2. And so this is 2/3 of electrons in difference. Now that temporarily should sound a bit strange. It is changing by 2/3 of electrons per lead, but we have 3 of them, right? We have 3 of them on the left, so we're going to have 3 on the right, and we're going to have to put that 3 in as our temporary coefficient, and then this 2/3 of electrons we're going to be multiplying by 3. And that should make us happy because 2/3 multiplied by 3 is going to give us our 2 electrons that we're actually dealing with there for the entire species. So the changes in electrons, we're talking about a loss of 5 electrons and a gain of 2 electrons. And so we want those to be equal. So again, our lowest common multiple is going to be 10. And we end up with our 2 factors that we are going to be applying to these species. So the manganeses are going to get our 2's, and so each of the species gets a 2 in front of it. Our lead species are going to get 5's in front of them. Now we have a temporary coefficient of 3, so we're going to multiply that by our 5, and so that is going to turn into our 15, and that gives us our balancing for our redox species. So let's drop that in, and our 15. And then that's it for our redox species. We've balanced them. It's not so bad in terms of using a non-integer oxidation number. And again, it will eventually work itself out in terms of being applied the entire group. Then we just have to balance by inspection. So I would probably go with the nitrogens first. So on the right-hand side over here, we know that we have 2 nitrogens times 15 is going to be 30 nitrogens. You can see why you wouldn't want to do this by trial and error. So 30 nitrogens on the right. Currently we have 4 nitrogens on the left. So we're going to need 26. Make sure I'm not missing anything here. That seems like a lot. 26 in front of that species in order to get our nitrogens. Then we've got to figure out either our hydrogens or our oxygens. Probably I would say maybe hydrogens would be the easier one to go with. We have 26 on the left right now as the only ones that we have on the left, and we have 2 on the right, so we're going to need another 24 over here. And if I added that up right, that should be, oh sorry, I did not add that up right because I have a coefficient of 2, so I'm not putting 24, I'm putting 12 waters on the right. And now clean that up a bit, and we have our balanced chemical equation. All right, sometimes less significant reactants or products are not going to be written in, and this is where you have the redox species happening in acidic or basic conditions, and so they may have just included the redox species, and you're going to have to add in some other species based on whether it is going to be in acidic or basic conditions. So let's go through the rules for balancing in acidic conditions, and we're going to use oxidation numbers to do that. So again, the redox species might be included in the reaction, but it might be missing some other things. And if it is in acidic conditions, the 2 things that it could be missing are water and hydrogen ions. So what we're going to do is we are going to add in water and hydrogen ions in order to complete the chemical reaction. We're going to add the waters first in order to get the number of oxygens to balance, and then we're going to add in hydrogen ions to get the hydrogens in the equation to balance. And again, by that point, once we have done that, all of the atoms should be balanced. And as a good way to check these to make sure they are balanced, you're never wondering whether you did the balancing equation correctly. As long as you can count, you can check your own balanced equations to make sure that they are balanced. And checking the charges is a good way to check because you're probably using the atoms while you're doing the question. So at the end, if you use the charges to check to see whether it's balanced, then you'll know you are correct. All right, so let's try balancing these using the oxidation numbers, and specifically in acidic conditions, which means we're probably going to have to add water and hydrogen ions in order to complete the reaction. And you can sort of see from this first one here, we are missing oxygens on the right. Like we have some oxygens on the left and there's nothing on the right that has oxygens at all. And it's because it's an incomplete redox reaction. So we're going to be adding water and hydrogen ions in order to fix that. First thing we want to do is we want to look at the oxidation numbers. So if we look at oxygen here, we know it's going to be -2, and there are 7 of them, so that's a -14. We know the sum is going to be -2, so essentially the chromium here has to come up with a +12 between the 2 of them, so each one must have an oxidation number of +6. Iron is an ion, so its oxidation number is its charge. And then that makes the right-hand side easy because chromium is going to be +3 and iron is going to be +3. So we know that the one whose oxidation number is going down is going to be going through reduction. So if we look at chromium, it starts off as 6 and it goes to 3. So we know that's reduction. And we have our oxygen, which isn't even on the right-hand side, so hopefully it's not doing anything. But our iron is going to be going from +2 to +3, which must mean it is losing electrons, it's losing negative charges, bringing its oxidation number up. So that is going to be our oxidation. So chromium's being reduced, iron is being oxidized. Now, in terms of number of electrons, if we look at our chromium, we're talking about 3 electrons, but there are 2 of them here. So what I will do is I'm going to put a 2 in front of this chromium so that I have 2 on both sides, and I'm going to apply that, so I'm talking about 6 electrons needed to do my reduction. My oxidation is just going to involve 1 electron to go from the +2 to the +3. It is just going to be losing that 1 electron, and there's only 1 of them, so we're good there. Now, in terms of factors, the lowest common multiple is going to be 6. So I'm going to multiply this by 1. I'm going to multiply this one by 6. And those factors should balance my redox species. So I'm going to now drop in my 6 in front of my irons and my 1 in front of my chromiums. Now this is a temporary coefficient. I'm going to multiply it by 1 so it becomes a permanent 2. And now I have my redox species balanced. What I then want to do is I want to add in some water on because there's 7 oxygens on the left-hand side. So I'm going to add in 7 waters on the right-hand side in order to get those oxygens to balance. So now my oxygens are good. But the problem is when I add these 7 waters, they contain 14 hydrogens. So I'm going to have to over here, let's see if I can get some room here. I pretend you can't see that. I'm going to have to add in 14 hydrogen ions to the left-hand side. Now my atoms should be balanced, and I can check. I should check my atoms to make sure they're the same thing. I've got 14 hydrogens on both sides. I've got 2 chromiums on both sides. I've got 7 oxygens on both sides and 6 irons on both sides. So all the atoms are balanced. Then the next thing that I can do is I can double check that the charges are going to balance out. So adding up charges, on the right-hand side I have 14 positives and I have 1 negative, so I'm down to +12, just to keep track of this. Then I have +2 times 6 is going to be plus +12 again. So I have +24 as my charge on the right-hand side. On the left-hand side, I have my 2 chromium ions, so that's going to be +6, plus the 6 times 3, 18 positives from my irons, and so that's going to give me +24 on the right-hand side as well. So my check works out, 24 and 24. The atoms are balanced, the charges are balanced, everything's good. Next one, let's try this just as a double practice. Clear up some room here. Same thing, oxidation numbers, and again, I'm going to ignore the oxygens, but what I will focus on is the chromium. So we've seen this guy before, so we know it's going to be positive 6. I'm going to ignore oxygen because I know it's not going to be my oxidation or reduction species. I have carbon here, and this is going to be plus 4. And this carbon here, I've got 4 at negative 2 each, and the sum is going to be negative 2, so that's going to be negative 8. So these are going to have to be positive 3, so they add up to be positive 6, and then the negative 8 will leave me a sum of negative 2. So I have my redox species, and again, we've got our chromium. It's going from 6 down to negative 3, or sorry, positive 3, so it is going to be a reduction. Our carbon, let's see if we can fit this up here as well, is going through an oxidation, and it's going, oxidation is the loss of electrons, so by losing those negatives, it is going up. In terms of electrons, we're talking 1 electron, but there are 2 of these, so we're really talking about 2 electrons. For our chromium, we're talking about 3 electrons, but again, there's 2 of them, so let's put a temporary coefficient of 2 in front of there. I forgot to do that for carbon. So temporary coefficient of 2 in front of there. So for the chromium, I'm talking 2 of them as well. So I'm going to multiply that by 2, and I will end up with 6 electrons for my chromium. And again, my lowest common multiple is 6. So my factor that I'm going to apply to my carbons is going to be 3. And the factor that I'm going to apply to my chromiums is going to be 1. So let's go ahead and put that 1 in front of my chromium. So this 2 becomes a permanent 2. And my 3 is going to go in front of my carbons, and this is now going to be 2 times 3 is going to be a 6. So my redox species are balanced. Now let's check our oxygens. On the left hand side we have 7 plus 12 is 19. On the right hand side we have 18, so we're going to have to add 1 over there, and that should give us our make sure I did that right there. Hold on. 6 is 12. No, that's not right. So we have 12 oxygens on the right, and what did we say on the left? 7 plus 12 is going to be 19, and so we have our 12, so we are going to need 7 of those on the right hand side of waters to get the oxygens to balance. The hydrogens are now 14, so let's look at a little bit of deja vu here. 14 hydrogens on the right hand side. Again, our questions in the way here. There we go. Barely see it. So we have 14 hydrogens on the right, and now we want to check to make sure that works. If our atoms balance out, then we can check our charges, and they should also balance out. So on the right hand side, let's get rid of the oxidation numbers so I can see this a bit better. On the right hand side, I've got positive 14. Minus 2 is positive 12. Minus 12 is going to, sorry, minus 6 is going to be positive 6, I believe. On the right hand side, the only thing I have with charges is going to be the chromium, and there's 2 of them. So the charge total on the right hand side is positive 6, left hand side. So my check works out. The atoms balance, the charges balance. I've got my balanced redox equation. All right, under basic conditions, it is the same idea, but so these same steps are the same as what happened under acidic conditions, but there's going to be one extra step. We are going to put in hydroxides in order to neutralize the hydrogen ions that would have been okay if we're under acidic conditions, but we're talking about basic conditions. So we're going to go through the same steps, which will probably give us some hydrogen ions that are there. And remember, these are positively charged hydrogen ions. But since it is basic, we are going to neutralize those using OH. So again, same thing. We're going to add water to balance. That's a 2. Water to balance the oxygens. We're going to add hydrogen, and then to neutralize the hydrogens, we are going to balance hydroxides. We're going to react these guys if they happen to be together. We'll react them and turn them into water, and then we want to make sure we cancel out any like terms between the left and the right hand side. Okay, so same step. First, oxidation numbers. So we have 0, we have -1, we have 0. I'm going to ignore the hydrogen, and so here is oxygen at -2. And as we can see, this isn't a complete reaction. We're missing some things, so we're going to be adding those in under basic conditions. Our reduction should see a drop in its oxidation number. And so if we look at oxygen going from 0 to -2, that is, it is gaining 2 electrons, but there's 2 of them on the left-hand side, so I'm going to put a temporary coefficient of 2, so I have 2 on the right-hand side, and so I'm really talking about a reduction. It is gaining 4 electrons. And my oxidation should see a increase in its oxidation number, so we're going from -1 to 0, that is 1 electron being gained. But I see there's 2 iodines on the right, so I should put a temporary coefficient of 2 iodines on the left. I'm going to multiply that by 2, so really I'm talking about 2 electrons going through my oxidation. Lowest common multiple is 4, so I'm going to put a coefficient of 1 in front of my reduction species. I'm going to put a coefficient of 2 in front of my oxidation species, and let's do that. A 1 here, a 1 is going to be applied here, so that becomes a permanent 2 now, because 1 times 2 is 2. I'm going to put a 2 in front of my iodine, and 2 times 2 gives me 4 iodines here. So I have my redox species balanced. Now I want to make sure I follow the steps. I'm going to add water to balance the oxygens. But I've got 2 oxygens on the left, I've got 2 oxygens on the right, so they're already taken care of. So the next step should be to add hydrogen ions to balance the hydrogens in the equation. I have 4 of them here. I don't have any on the right-hand side. So I'm going to add 4 hydrogen ions on the left-hand side in order to balance those 4 that are in the water. Now, because if we were under acidic conditions, we'd be done. That'd be it. But since we're under basic conditions, we're going to add in an equal number of hydroxides to balance, neutralize those hydrogens. But if we add them to the left-hand side, it would throw off the balancing of our atoms. So we're also going to add the same number. We added 4 to the left. We're going to add the same number to the right-hand side. So 4 on both sides. Now, these 4 hydrogens and 4 hydroxides, they are going to neutralize and form 4 water molecules. So really, I have 4 water molecules on the left, and I have 2 on the right here. So really, we can simplify that. We can cancel out those 2 and change this 4 into a 2. So let's clean this up a bit. So those 2 waters, let's write them down here. 2H2O. And we should now have all of the atoms balanced, but again, as a check, we should check charges. So if we look at the left-hand side, let's check atoms too, just because that was a little bit much. So again, that water's gone. So on the left-hand side, we have 4 hydrogens. On the right-hand side, we have 4 hydrogens. On the left-hand side, we have 2 oxygens and 2 oxygens. That's 4. On the right-hand side, these waters are gone. So we have 4 oxygens, 4 on the left, 4 on the right. We're good. 4 iodines on the left, 4 iodines on the right. Perfect. So the atoms balance, and we can now check charges. Let's add them up separately. So here is -4 from the hydroxides. And if we look on the left-hand side, the only thing that has charges is the 4 iodines. So we have -4 on the left-hand side, -4 on the right-hand side. The charges balance. This is our balanced equation. And that is redox balancing using oxidation numbers, temporary coefficients, non-integer oxidation numbers. What else did we do? We looked at acidic conditions and basic conditions, and now you should be able to balance any redox equation either using oxidation numbers solely or using oxidation numbers in acidic or in basic conditions. Here's to help you remember what to do when you're balancing in acidic or basic conditions. So water for the oxygens, hydrogens to balance the H2O. If it is basic, then to both sides, hydroxides will go.